Welcome to Pre-Calculus. Today we will investigate finding sums of infinite geometric series. Let's take a look at a couple examples that are presented just as series in a row. So not in sigma notation yet. I've got this one here, 625 over 64 plus 125 over 16 plus 25 over 4 plus 5. And initially, my goal is to decide whether or not the geometric series converges or diverges. That's a prerequisite for being able to find the sum of an infinite geometric series. And what we got to note is that for that to be possible, I have to have a certain criteria in place. And the criteria that we have for convergence of an infinite geometric series is that the common ratio has to be smaller than 1. The conversion of an infinite geometric series, the way that we define that is that the R value, the common ratio, and we do want to say it's absolute value. So if it's negative or positive, if we take the absolute value, if it's less than 1, the series will converge. And if that's the case, then we can actually find the sum. If it's not less than 1, what we would say it's divergent, and we can't find the sum because in a way we see that the series is getting bigger and bigger and bigger, really headed towards infinity. So what we want to check for here is what's the R value. So I'm going to take two pairs, well, one pair, two terms here in the series, and I want to find the common ratio. So remember, we just take the second term, divide it by the first. So with fractions, it's a little tricky. I'm going to divide 125 over 16 by 625 over 64. And initially, that's hard to solve. I don't quite know how to evaluate that. But remember, I can convert this to multiplication. This is the same as 125 over 16. And I can convert the division to multiplication. And then all I have to do is invert or find the reciprocal of the denominator. So that becomes 64 over 625. And then I just want to see if I can reduce with these terms that are at the corners. So 64 divided by 16, I know 16 times 4 is 64. So I can cancel the 16 and leave a factor of 4 where 64 was. And also 625 divided by 125 is 5. So we have for our common ratio here 4 over 5. Let's see if that's consistent. I'm going to take the next pair of terms in the series. So again, 25 over 4. And the same setup, I want to divide by the previous term, but again, I'm going to convert to multiplication and then multiply by the reciprocal of 125 over 16. So that's going to be 16 over 125. Again, we want to reduce that. 16 divided by 4 is 4. 125 divided by 25 is 5. And we see that that is confirming what we saw with our first division. So what we need to check is the last pair. So that's going to be 5. I'll put over 1 times the reciprocal of 25 over 4 is 4 over 25. Not as much to cancel here. The 1 really is redundant. 25 divided by 5 is 5. And so we see with this last division that that is in fact our common ratio, 4/5. So we'll say for this series, which I know is infinite, by the way, because of this ellipsis. The dot, dot, dot tells me that it goes forever. It doesn't end. So my R value is 4/5. And then what I want to compare is how does 4/5, and I do want to take its absolute value since that's how we define convergence. How does it compare to 1? Well, if I look at the numerator, it's smaller than the denominator. This is a value about, in fact, exactly 0.8. That's less than 1. So therefore the series converges. So in a moment, what we'll see is with a series like this one, I could in fact find the sum. This is a prerequisite to finding the sum to see whether or not the infinite geometric series converges or diverges. Well, let's take a look at an example that's given not in the list form, but in sigma notation. So you can see definitely here how this one is an infinite geometric series. It's got the infinity for my upper limit. It doesn't actually end at a number, it just keeps going forever. And we could think about what the first term, really multiple terms in this series look like just by evaluating using this explicit rule. So we do start with an I value of 1. So if I plug in that I value, I'm going to have -2 times -4 to the power of 1 minus 1. So that's power of 0. Anything to the power of 0 is 1. -2 times 1 is -2. So that's my first term. And since it's a series, I'll put plus instead of a comma. Let's just calculate our next term just so we can see how the common ratio works. So again, I take -2 times the base -4 to the power now of 2 minus 1. So that's going to be power of 1. -4 to the power of 1 is -4 times -2 is +8. We'll do one more just to see how the series is forming. So plus -2 times -4 to the power of 3 minus 1. 3 minus 1 would give us an exponent of 2. -4 squared is 16. 16 times -2 is -32. And then if I was in the series and I just wanted to say it's going forever, I would write plus and then the ellipsis, ... So what I'm seeing is that my common ratio, if I divide 8 divided by -2, -4, -32 divided by 8, -4, well, that's recorded within the sigma notation in that explicit formula. Remember that base is the common ratio. So I'm going to identify R here as -4. So then I want to make a claim, the absolute value of -4. So that's equals exactly +4. I want to compare it again to 1. So 4 is greater than 1. And let's think how we could classify this series based on that R value. It's bigger than 1. Therefore, the infinite series diverges. The infinite geometric series diverges. So here's an example of a series that we could not find the sum for because its R value has an absolute value bigger than 0. I'm sorry, bigger than 1, so that it diverges. Definitely, in sigma notation, you can just pull it out. We did expand the series here, but that's not required. All right, so let's then kind of face this main task of this lesson, which is to evaluate the sum of a geometric series that is infinite. So here I've got one again in the list form. I got 7.2 plus 2.88 plus 1.152 plus 0.4608. First thing I want to do is decide whether or not I can actually find the sum. Is it convergent or is it divergent? So again, I take pairs in the series and I just want to divide the former by the previous. So I'm going to take, and let's take 2.88. So I'll use the calculator here on this screen since we just need simple division, divided by 7.2. And that gives us a common ratio between the first two of 0.4. Let's keep going. 1.152 divided by the previous term, which again would be 2.88. And that gives us, again, ratio of 0.4. Let's see if that's a fully common ratio. So again, I'm going to take and divide, in this case, 0.4608 divided by the previous term, 1.152. And we see that that equals, again, 0.4. So I can see that this is a geometric series. It has a common ratio for my division of 0.4. And the absolute value of 0.4 is 0.4. And when I compare that to 1, that's clearly less than 1. So this series converges. This series converges. So once I identify that it is convergent, I can proceed with finding its sum. Now, with finite sums, we literally can just add up the terms. We did come up with a nice general formula for finite sums. When I consider an infinite series, there's no way that I can add up all the terms because of the nature of the series. It's infinite. But we do also have a formula that we could apply. So let's pull that formula. So the sum of an infinite geometric series is given by this formula. We'll call it S for sum, and we'll put the subscript infinity just to indicate it's the sum of an infinite geometric series equals the ratio of the first term, a sub 1, over 1 minus the common ratio. So even though it's infinite, the formula we've got for the sum of the infinite geometric series is simpler than the formula we have for the finite one. Well, all we got to do is identify what my first term is and the common ratio. Common ratio we've already found to be 0.4. So for us, we'll go ahead and fill in here. We're going to have 1 minus 0.4 in the denominator. And then the last piece that I need is the first term. So my a sub 1 here is going to be 7.2. And that is all I need to calculate. So let's take that over to Desmos. Since I've got some mixed calculations here, it'd be easier to calculate there. And let's find that sum. So I'm going to create the fraction in Desmos, put 7.2, the first term, over 1 minus 0.4, the common ratio. And right away, I have a full sum for that geometric series. It all adds up to 12. So that example definitely shows how we can use this formula. Let's take a look at one final example here that involves a series represented in the sigma notation. So again, I've got this, I know it's infinite because of this upper infinity. Tells me that the series, whatever it is going to head all the way up to an infinite number of terms. So I do want to just create the first few terms so I can see what it looks like. So we'll take the first term, it's going to be negative 1/2 times the base 1/3 to the power, my first m value in my index is 1, so 1 minus 1. So again, that's the power of 0. 1/3 to the power of 0 is 1. Negative half times 1 is negative 1/2. Let's calculate the next term. So I'll put plus, so again, negative 1/2 times base 1/3 to the power now of 2 minus 1. 1/3 to the power of 1 is 1/3 times negative 1/2 is minus 1/6. We'll calculate the third term, so plus negative 1/2 to the, times 1/3 to the power of 3 minus 1. So 1/3 squared is 1/9. 1/9 times negative 1/2 is negative 1/18. So I can see the way that this series is going, it's really just multiplying times 1/3 from that first term, negative 1/2. So I'll put minus and then the ellipsis just to indicate that that is infinite. So I do want to check on my R value. Definitely my R value, remember from the formula, is that base. So my common ratio is 1/3. When I compare the absolute value of 1/3, which is 1/3, to 1, I see that 1/3 is less than 1. Therefore, the series converges. So I can actually find the sum for this series as well. Even though this one is presented within the context of sigma notation, we can still find the sum pretty easily. So we'll pick up the sum formula, S sub infinity. Just to put it in general terms again, first term a sub 1 over 1 minus the common ratio. So we'd already found the first term, a sub 1 is negative 1/2 over the common ratio, or I should say 1 minus the common ratio, which was 1/3. So lots of fractions here. This one we can probably calculate just manually, since fractions are in a way easier than decimals. Negative 1/2 over 1 minus 1/3 is going to be 2/3. So again, I got that fraction within a fraction set up, the complex fraction. So that's equivalent to negative 1/2. Convert division to multiply, and then give the reciprocal of the denominator 2/3. So times 3 over 2. And that's going to be negative 3 over 4. So the whole series adds up to negative 3/4. Hard to imagine that we could actually find the sum of something that's infinite. But again, because the R value is smaller than 1, it's possible to do it. Thanks for joining for these 4 examples investigating finding the sums of infinite geometric series. See you soon.